In the previous lecture we discussed about Otto cycle, and today we will discuss about diesel cycle. From the name itself it is clear that this cycle, thermodynamic cycle, is used to model the thermodynamic performance of diesel engines, and that is why the name diesel cycle. So, we will draw the PV and TS diagram and try to identify what is the difference between this cycle and the Otto cycle. So, process 1 to 2 reversible adiabatic compression, this is same for both Otto cycle and diesel cycle. The major difference between the Otto cycle and diesel cycle, and perhaps the only difference, is that the heat addition in diesel cycle is considered to take place at constant pressure instead of constant volume. So, 2 to 3 constant pressure heat addition. So, constant pressure heat addition means it will be a horizontal line here. So, after the constant pressure heat addition, so this is P equal to constant. There will be the expansion or the power stroke. So, 3 to 4 reversible plus adiabatic expansion. And then from 4 to 1 you have constant volume heat rejection. See, the heat rejection is not done at constant pressure for the reason that it will increase the stroke volume to an extent that it will be a bulky cylinder for, too bulky for internal combustion engine purposes. So, although the heat addition is constant pressure, but heat rejection for automobiles is traditionally constant volume. Here I have purposefully drawn this line steeper than this, because in a TS diagram the constant volume lines are steeper than constant pressure lines. Now, we are going to analyze the efficiency of this cycle and compare that with Otto cycle. That is one of the tasks that we will do. So, what is QH here? Without referring to individual systems for writing the first law of thermodynamics, we will simply now will write that the heat addition is from 2 to 3. So, QH is U3 minus U2 plus W23, right. Straight away this we are writing. So, one of the major assumptions in the air standard cycle, which in the previous lecture I forgot to mention, but you also add it, that you neglect changes in kinetic energy and potential energy of the working fluid, because we are writing these expressions neglecting the changes in kinetic energy and potential energy, although that is not what we explicitly tell always. For thermodynamic purposes, the thermal energy contribution is usually much more significant than the kinetic energy potential energy contribution. So, this will be Cv into T3 minus T2, and what is W23? So, this is integral PdV from 2 to 3. So, P into V3 minus V2, pressure is constant, right. So, the fuel injection process, which is typical to the diesel engines, is such that during the fuel injection, so the difference in paradigm try to understand. In the previous cycle we were trying to model the combustion in a already mixed air and premixed air and fuel in the Otto cycle. So, here we are considering that the air is highly compressed and the fuel is injected. So, once you do that, the fuel injection process during which this chemical energy of the fuel is input to the highly compressed air, you will have roughly a constant pressure heat addition process. So, that is why this difference between the heat addition processes in Otto cycle and diesel cycle. So, now PV3 this is as good as RT3 and PV2 this is as good as RT2. So, you can write this as Cv plus R into T3 minus T2. So, that is nothing but Cp into T3 minus T2. Okay. What is QL? QL is nothing but, now it is a constant volume process. So, Cv into T4 minus T1. Remember, heat transfer sign wise this is negative heat transfer, but when you are writing QL for the purpose of calculating efficiency, it is already the mod, it is already the magnitude. So, we have to write T4 minus T1 and not T1 minus T4. The efficiency, we will calculate the efficiency in this side. Is equal to 1 minus QL by QH. So, this is 1 minus Cv into T4 minus T1 by Cp into T3 minus T2. Cv by Cp is 1 by gamma. Just like the previous example of Otto cycle, we will extract T1 by T2 here, we will write T4 by T1 minus 1 by T3 by T2 minus 1. Now T4 by T1 we can write T4 by T3 into T3 by T2 into T2 by T1, right. Now T1 by T2 or T2 by T1, what is T2 by T1? V1 by V2 to the power gamma minus 1. So that is R to the power gamma minus 1. And what is T3 by and what is T4 by T3? Is equal to V3 by V4 to the power gamma minus 1. V3 by V4 is V3 by V2 into V2 by V4. V2 by V4 is same as V2 by V1, right, because V4 is same as V1. So this is, now before that what is V3 by V2? V3 by V2 we call as cutoff ratio or RC. So this is a new definition. So RC to the power gamma into 1 by R to the power gamma minus 1, where RC is V3 by V2 is equal to cutoff ratio. Why this is called as cutoff ratio? Because this is the volume ratio at which the heat addition is cut off, otherwise you would have indefinitely continued. So then let us write this T4 by T1 as T4 by T3 is RC to the power gamma minus 1 into 1 by R to the power gamma minus 1. What is T3 by T2? P2 V2 by T2 is equal to P3 V3 by T3, right, and P2 is same as P3. So T3 by T2 is equal to V3 by V2, which is again equal to RC. So this becomes T3 by T2 is equal to RC, and T2 by T1 is R to the power gamma minus 1. So T4 by T1 becomes RC to the power gamma. Therefore, the efficiency expression what is the efficiency expression? 1 minus 1 by gamma into T1 by T2, T1 by T2 is 1 by R to the power gamma minus 1 into T4 by T1 minus 1. So RC to the power gamma minus 1 divided by T3 by T2 is RC, right. So, essentially the efficiency expression is the Otto cycle efficiency expression multiplied by a correction factor. Right. With this basis, now let us compare the Otto cycle with this cycle. So, for the Otto cycle we have this term multiplied by, so eta is equal to 1 by r to the power gamma minus 1, this multiplier is not there. So, let us see whether this multiplier is greater than 1 or less than 1 or what it is. So, for that you just let RC minus gamma 1 is equal to x, just take it. So, RC is equal to 1 plus x. So, RC to the power gamma minus, so not, so this minus 1 is full minus 1, not RC to the power gamma minus 1. So, RC to the power gamma minus 1 is equal to 1 plus x to the power gamma minus 1. 1 plus x to the power gamma is, you can expand in the binomial series. So, 1 plus gamma x plus gamma into gamma minus 1 by factorial 2x square, like that it goes on, minus 1. So, this is gamma x plus higher order terms. So, RC to the power gamma minus 1 by gamma into RC minus 1 is equal to gamma x plus whatever by gamma x, right. So, this is this plus whatever term which is greater than 0, right. So, this multiplier is a multiplier, oh sorry, greater than 1 not 0, okay, greater than 1, right. So, 1 plus something, not greater than 0, so greater than 1. So, then this multiplier being greater than 1, so what is the efficiency that you expect? You are subtracting a number magnified by a factor greater than 1. So, this should be less as compared to what is there for the Otto cycle. So, the conclusion is for the same R, eta Otto should be greater than eta diesel. But this is very misleading, you know. Why is this very misleading? This is misleading because same R is not a good basis for comparison. Same compression ratio will not be the case for Otto cycle and diesel cycle, because you are solely compressing air and not air fuel mixture in the diesel cycle. You can go up to very large compression ratio, and at very large compression ratios the diesel cycle might have an efficiency which is quite large. So, same R may not be the same basis for comparison, but hypothetically if it would have been same R, then Otto is greater than diesel. So, but this mathematical way of comparison can also be substituted by a more physical way of comparison. So, I will try to give you two examples of comparison of Otto cycle and diesel cycle before we call it a day today. Okay. So, the first, so for any comparison there should be a basis for comparison. You should not compare apple with an orange. So, for common basis let us say for the same R and same QH, when heat transfer is given as a basis, it is better to use the TS diagram, because heat transfer information is directly available from TS diagram, work done information is directly available from the PV diagram, but interestingly the area under the PV diagram is same as the area under the TS diagram for a cycle, because cyclic integral of heat equal to cyclic integral of work, and area under the TS diagram is cyclic integral of TdS, which is cyclic integral of del Q. So, area under the PV diagram is same as the area under the TS diagram, is same as the net work and is same as the cyclic integral of heat. All these things are equal if it is an internally reversible cycle, because if it is not an internally reversible cycle you cannot write del Q equal to TdS. So, area under the TS diagram is equal to integral of del Q, cyclic integral of del Q, that you can write only for an internally reversible cycle. Similarly, area under the PV diagram is same as the net work done for an internally reversible or quasi equilibrium process or a collection of quasi equilibrium processes. So, these things we must remember. So, same R and same QH. Same R means if you start with the point 1, the state point 2 will be the same, because T2 by T1 is governed by only R and gamma, right. Then, so with white line I will draw the let us say the Otto cycle. This is what? This is constant volume. And with a red color I will draw the diesel cycle. So, from 2 you will have a constant pressure line. So, if you have a constant pressure line, constant volume line is steeper than constant pressure line. So, constant pressure line from 2 will go like this, and heat addition being the same, the area under 2 to 3 represents the heat addition process in the TS diagram. So, from 2 to 3 whatever is the area under that, that is the heat transfer during heat addition for the Otto cycle. For the diesel cycle, because this line is going below, to compensate for this loss of area it should go further towards the right to make the area under 2 to 3 same as area under 2 to 3 prime. And then, so if you reject heat with constant volume, then it is a basic continuation of 1 to 4 diagram. Then you see for the same QH which is having more QL, for the Otto cycle this is the QL, and for the diesel cycle you have this additional QL, right. So, for same QH you have more QL for the diesel cycle, that means its efficiency is less. So, the mathematical form that for same R the efficiency of auto will be more than efficiency of diesel, we can justify this just physically from the TS diagram. But this may not be a good basis for comparison, as I have already mentioned that same R may not be a very practical way to look into it. So, let us say we give a constraint same P max and T max. If you have same P max T max, see P max and T max is occurring at state point 3, right. So, if P max and T max is occurring at state point 3 and if you specify these two states, V max is also specified because PV equal to RT, that means for same P max T max, that is the combination of P max T max, you could in principle fix up the state point 3 as unique state point for both Otto cycle and diesel cycle. So, let us so this is the Otto cycle, with the white line we have drawn it. So, with the same state point 3, now, so with the same state point 3, the constant volume line is steeper than constant pressure line, right. So, the constant pressure line will be less steep and it will go something like this. So, this is P equal to constant, it will go less steep than constant volume line, and then if you keep 4 and 4 prime and 1 prime same, the point 2 prime will be above the point 2, right. The point 2 prime will be above the point 2 because of it being less steeper. So, area, the heat rejection being the same, heat addition is area under the TS diagram from 2 to 3. Because 2 dash is above 2, you have an extra area representing extra heat addition for the diesel cycle. So, for same heat rejection, if you have more heat addition, you have more efficiency. So, this is a more logical way of comparing the two cycles, and here you can see that you have eta diesel greater than eta auto, because the practical engine constraints are most of the times dictated by what is the maximum pressure it can withstand, what is the maximum temperature it can withstand, and so on, and not intrinsically by the compression ratio. So, if somebody asks you a question, does Otto cycle have more efficiency than diesel cycle, or does diesel cycle have more efficiency than Otto cycle? The first return question that you must ask, what is the basis for comparison? What are the parameters that you are keeping fixed? So, depending on what you are keeping fixed, you will have different answers, right. In this case you have eta auto greater than eta diesel, but in the case 2 you have eta diesel greater than eta auto. Now, finally, I will give you a small note. What does a real internal combustion cycle, internal combustion engine cycle look like? Is it auto, is it diesel? In practice, the heat addition is neither a constant pressure heat addition nor a constant volume heat addition. So, it could be perceived as a combination of constant volume and constant pressure heat addition, and there is a cycle that takes that into account. I will not get into the details of that cycle, but I will just draw the maybe PV and TS diagram of that cycle, that is called as a dual cycle. So, dual cycle is a combination of Otto cycle and diesel cycle in a sense that part of the heat is added at constant pressure and part of the heat is added at constant volume. So, if you draw the PV diagram, so you have compression, then heat addition partly constant volume and partly constant pressure, but heat rejection definitely at constant volume. And the TS diagram, so first constant volume curve which is steeper and then less steep constant pressure curve, then reversible adiabatic expansion and then heat rejection. Okay. So, to summarize, we have discussed two important air standard cycles, one is the Otto cycle, another is the diesel cycle, and we have compared their efficiencies. But air standard cycle is not just restricted to cycles for internal combustion engines. We could have other applications where air standard cycle can be applied. One such application is the gas turbine cycle, for which we consider the Joule cycle or the Brayton cycle, that we will study in the next lecture. Thank you.